A really important skill for exam 2 is the ability to look at an equation and then determine what line what we should plot to make a line, and then how we can interpret the slope and the intercept of that line to learn things about our experiment, to learn things about that model. So here's an example from exam 1 content just to show how that process works. For the photoelectric effect, if we solve that for kinetic energy, we get an equation like this. Kinetic energy is h nu minus w. Then an experiment might be, if we're trying to measure Planck's constant and the binding energy, we shine light of different frequencies on our metal surface and then measure the kinetic energy of the ejected electrons, right? We're shining light of different frequencies. Again, just that sort of basic science content, sort of high school science, right? We control the frequency of the light. So that's our independent variable, frequency of the photon, or the frequency of the light that we shine on the sample. Then the dependent variable, if we look at what we're measuring, right, that's over here, we're measuring the kinetic energy. And so that's right here, the dependent variable is the kinetic energy of those electrons. And we can see that based on this equation, we have the kinetic energy here on the left, the frequency of the photon on the right, and what we need to do is just check that that is going to be linear, and in this case it is, because kinetic energy is going to be equal to h times nu photon minus w, and so this is the equation of a line. If I compare that to y equals mx plus b, and just sort of compare terms, I can see that my minus w is my plus b. My x and y, right, my x variable is nu photon. My y variable is the kinetic energy of the electron. And h, Planck's constant, is equal to my slope. Because the way this, y equals mx plus b equation of a line works is that the slope is, right, the thing multiplied by the x variable is the slope. So in this case, that's h in my model. And so, yeah, this is a line, right? For every amount my energy of my frequency of photon increases, the kinetic energy will go up by an amount h times that frequency. So in this case, just based on how that equation looks, it is going to be linear if we just plot kinetic energy of electron on the y-axis versus nu photon on the x. We can see that over here now. So I've got kinetic energy of the photon on the y, photon frequency on the x, and it is linear. We have a very high r squared, and we now have in our model, right, that's this using model variables, right? Just these comparisons that we just did over here is, okay, if this model is working, the slope m is going to be equal to Planck's constant h. The units on the slope should match. Remember that the units here for the slope is sort of delta y over delta x, so that's going to be the y unit over the x unit. So in this case, the units on the slope here, joules seconds to the minus 1, joules over seconds to the minus 1 is the y unit over the x unit, and that would give me joule seconds. If we look at the y-intercept is just a value on the y-axis, so the y-intercept units are always just going to be equal to the y unit. So this is, the y-intercept is a value on the y-axis, so the y-intercept has the same unit as the y-axis, which is joules. Now, according to the model variables, when we plug that in, the intercept is going to be negative times the threshold negative times the threshold energy, right? But the idea is for any equation, we can, find a form that looks like this, where it looks like the equation of a line, and then use the slope of the line and the intercept of the line to learn things about our model. So in this case, for example, what's the threshold energy of the metal? Well, I know the threshold energy is equal to negative of, I have the slope is negative the threshold energy. So if I take and plug into that equation, I have again, remember, y equals mx plus b. So I have b is equal to negative 3.80 times 10 to the minus 19. Again, my unit there is joules, even though Excel doesn't give me the unit there. We know it just from the units on the y-axis. And that's equal to negative w. So if I just, I have a negative on both sides, I can multiply everything by negative 1 and get 3.80 times 10 to the minus 19 joules is equal to w. And yeah, this is something we do for all sorts of different equations on this sort of second half of exam 2 content. We have a bunch of equations where we look at the equation, compare it to a line, and then learn things about our reaction from plotting these lines. The next example of this is for the Arrhenius equation that we covered in class previously. We showed the sort of form of that equation that looks more like this, where we originally showed this equation, which is, K equals a e to the negative ea over RT. And that equation, that equation is not linear at all. We have this exponential, really very, very nonlinear. But we have the same basic idea. The idea is that we're going to determine the activation energy and pre-exponential factor for a reaction. And to do that, we're going to measure the rate constant of the reaction at different temperatures. And from that information about how the rate constant depends on temperature, we should be able to determine the activation energy and the pre-exponential factor. So use the sort of equation here and see what you think you can get for what is the independent variable, dependent variable linear plot, slope and intercept. Take a second here, you can pause and see if you can do any of those on your own, and then I'll show the solution. It's really the same process as for the previous one. Anytime you have an equation, it's the exact same sort of process to determine how it relates to our linear model. Okay, so then sort of showing what this looks like. Independent variable is the rate constant K. That's, dependent variable, measure the rate constant at different temperatures. Independent variable is the temperature. That's what we're controlling. Dependent variable, rate constant, which is K. Now, we said before, K versus T isn't linear, but if you see this new rearranged form of the equation, ln of K is equal to negative EA over R, 1 over T, plus ln of A. And so this actually does look like y equals mx plus b. If I put it next to it, I can do that exact same correspondence here. 1 over T is in the position of x, ln of K is in the position of y, negative E over R is in the position of M, and ln of A is in the position of B, right? And again, the idea is we can just say those things are equal. If this model is working, that's what we're going to have. The linear plot here is ln of K versus 1 over T. The idea is it's always going to be something related to my dependent variable on the y versus something related to the independent variable on the x. And in this case, when we do this, we should get a line. Even though this equation isn't linear, when we use these natural logs, we now get a nice linear equation, a nice linear plot. That's what we see here in our experimental data. Again, doing that equality here, the slope m is, according to the model, if it works, negative EA over R. Just seeing what corresponds to what. Similarly, the y-intercept b we can see is equal to ln of A. We'll do this again for several more equations here when we come back from break, but it's important to sort of know how that process works. Okay, the next thing is the units. Again, for the y here, it's always delta y over delta x, so it's is equal to sort of our slope, right? Change in y over change in x. Y unit over x unit. One thing you may have not realized or remembered is that if I take ln of k, that is going to be unitless. So just like absorbance was unitless in lab, ln of k, whatever the units of k are, once I take the natural log of it, it ends up unitless. So this right here has no units, or we can view that as sort of 1 as the y unit, and then the x unit is 1 over Kelvin. And now if I take my overall unit, it's 1 over Kelvin, which is just equal to Kelvin. So the units here are Kelvin, B ln of A. The units there are, in this case, whatever the y unit is, so this is unitless. The important thing to remember is that when you undo this to solve for A, what we'll have to do is remember that the units here are the exact same as the units on K. So that was something we went over the first time we used the Arrhenius equation. Same units as K for the pre-exponential factor. If we were being a little bit more precise here, sometimes we would put ln of K. Sometimes we would write something like ln of K over seconds to the minus 1 or something like that. Okay, now that we have sort of the Arrhenius equation listed out here, take a couple minutes here to do the example. So what is the activation energy and pre-exponential factor for this process given the linear plot and the data there? Okay, so here's the solution. First, the activation energy. We can get that from the slope m, because activation energy is in this equation. So I plug in, I have m is equal to negative EA over r. M is the slope, that's going to come right off of our graph here, negative 6240. So I want to solve for activation energy, so I can just multiply both sides by to solve for EA. I'll just take negative of both sides, so negative m. So I'm going to multiply by negative r on both sides. That will make this positive, and it will cancel the r on the bottom. And it'll cancel my negatives there. So negative mr is equal to EA. Negative m is 6240. Again, Excel doesn't give us a unit there, but I know the units there are Kelvin from the units on the graph. And then m is negative 6240. Then there's another negative out front, and r is 8.314 joules per mole Kelvin. And that's my activation energy. So that all sort of should check out. This is negative times a negative, which is a positive, and I just get 6240 times 8.314. Okay, then, so we get 51,880 joules per mole is our activation energy. Kelvin canceled here, so we did get the right units. A lot of times we'll report this in kilojoules per mole because it's a more convenient number. So the conversion there, 1,000 joules is 1 kilojoule. And so we can think about that, moving the decimal place 3 units, 1, 2, 3. For a factor of 1,000, 51.9 kilojoules per mole is our activation energy. Okay, same idea for the pre-exponential factor. For the pre-exponential factor, we have, let's see, we get that from the y-intercept. So ln A is equal to B, and B was 19.2 is equal to ln of A. Now this is where we need to remember our sort of logarithm rules. Remember that if I have like ln A is equal to B, to undo the natural logarithm I take e to both sides. So e to the A is equal to B. So here I take e to both sides, and I get A is equal to e to the 19.2, which is equal to, I get 2.18 times 10 to the 8 there. Again, let's say that I said it was a first order process, so the rate constant was in 1 over seconds. That leaves this here as seconds to the minus 1. Whatever my units on K are going to be my units on A. Okay, so we'll pick up here with sort of integrated rate laws after break. There's some of these homework questions on determining the activation energy and things from this plot of ln of k versus 1 over t, the Arrhenius plot. The last thing that will be on the homework here for after break is just this part right here. We won't go through all of these equations. We'll do that in class after break. But it's important to note, just so you start getting ready for this, that 0th order, it turns out that it's A versus T is a linear plot, because this is sort of going to be the key thing to remember here for the exam. A versus T is linear for 0th order. For the first order, it's ln of A versus T is linear. And for second order, it's 1 over A versus T is linear. And so there's a couple questions just asking about that piece of it on the homework, and that's something just that's good to start remembering now. And then once we have that, we'll be able to assign all of these equations to their appropriate place, and you'll be able to use them in class after break to get ready for our quiz and exam coming up after break. So yeah, have a good break, everyone, and let me know if you have questions, and see you when you get back.